All right, let's talk about a couple of things about lecture 3. This is where we finished off. I just wanted to give a really quick refresher course on pH, since now you had a chance to do a little bit of pH measurements in the lab. And we've already done this question, so I'm going to do it really quickly. So just a reminder of the formula of pH is that it is the negative log of the hydrogen ion concentration. So in this case here, it's basically crunching the numbers into your calculator. And like I said, it's always worth it to figure out how your calculator works for these kind of things, because I find myself, which happened to me last lecture, I had a new calculator and yeah, it took me a while to figure out how to work it. And of course, it was a little embarrassing in class not being able to know how to work my calculator. So in this case here, I'm punching that in on my main calculator. I punch in the number. Then I press log. I know on the new calculator I found, it was the exact opposite. I had to press log first and then punch in the number, which, you know, of course, makes things a little extra weird when I'm trying to sort it out. So the answer here is of course 2.6 when I punch that in. So this here is pH of 2.6 is acidic, and hopefully that's pretty straightforward because vinegar is basically a solution of acetic acid, which is a weak acid. The other type of calculation that you should be familiar with is doing the exact opposite. So basically manipulating the pH formula in the other direction so that if you have the pH, you can figure out the hydrogen ion concentration. And so in terms of this formula manipulation, it looks something like this. Oops, sorry about that. I'm just going to scratch that out. 10 to the minus pH. And that's something on my my regular calculator. There's actually 2 ways to do it. And I still haven't figured out how to do it on my new calculator. But the one I have in my office is another story. Again, it has a different way to do things. So always take a look at how you're going to do this. So the answer here and is 6.3 times 10 to the minus 7. So in this case here, it is slightly acidic. Slightly acidic. Okay, so that was, like I said, just a quick review of how to do these questions, which is related to lab 1. Okay, so more on pH. How do we measure pH? There's actually a lot of ways we can measure pH. pH, of course, is the hydrogen ion concentration. And there are a number of methods to do so. These are the ones that you're probably familiar with all of these to some degree. Last day in the lab, of course, we use the pH strips and the pH meter. The pH meter is going to always be more accurate because you're calibrating it. And of course, you're not distinguishing between, you know, really close shades of orange or pink or something like that, you know, it can be almost a little bit subjective in terms of, you know, one person says, okay, that's closer to a 5. The other person might say that's closer to a 6. Although pH strips, when in a pinch, they're quick and easy and they're super cheap. So a lot of people might have them for things like fish aquariums and whatnot, because of course you're not going to invest in an entire pH meter, but pH color strips are kind of good enough. The color strips, of course, are based on indicator chemicals, and I've got this this little chart that I found that shows a whole bunch of these indicator chemicals, and I'm assuming that's what you used for your titration in Chemistry 101 with some sort of indicator. Often when people are trying to pH to 7, it depends on exactly what pH you're trying to get to, but methyl red and phenolphthalein are pretty common, and so on. Again, it depends on what pH you're actually trying to get to. And the last method on here are titrations, and I'll come back to that. My plan is to kind of show you a sample sort of titration here in a minute, and we'll get back to that. And that's something where you're quantitating the amount of acid or base in a solution using a titration method, right? So before we kind of get into titrations, I just want to talk a little bit about acidity. So acidity, of course, there's different definitions, and you probably talked about in chemistry in terms of the Lewis definition of an acid or a base and the Bronson-Lowry definition of acid and a base. But in water quality, and in fact, in most biological situations, we're looking at basically a measure of the hydrogen ion concentration. Measure of hydrogen ion concentration. When you have lots of hydrogen ions, it's something is acidic. Chemical way to define it is also the capacity to neutralize or react with a strong base. And that's what you can see here on this slide, right? And so, that's kind of just thinking about how it's reacting, right? But often, like I said, you're really looking at hydrogen ion concentration because in aqueous solutions, that's really a very good definition. And it turns out that in environmental samples, acidity is not just related to acids, but also very strongly associated with carbon dioxide. And so I guess that's the first question here. And actually, I usually write some formulas on the board here, and I'm gonna, I think I actually have this on my next slide here. So how is carbon dioxide acidic? And this is related to that last exercise you did in the lab. Remember, you were blowing carbon dioxide bubbles in. And so carbon dioxide actually reacts with water like this. So carbon dioxide reacts with water, and it does this naturally. And this is what we get. So if anybody knows what that is, it is carbonic acid. So carbonic acid, when it gets when it's in solution, it disassociates. And so what we do is we get our protons. And of course, that is acid. And we get bicarbonate. And bicarbonate, technically, you could call it your conjugate base. We're just going to call it bicarbonate. And bicarbonate as well can also continue to disassociate, and you're going to get more acid. And we get carbonate, which is like this. So for most practical purposes, and I'm not going to write this down here because I'm running out of space, but for most practical purposes, when we're looking at the acidity in water, we're looking at CO2, bicarbonate, and carbonate. Now, of course, bicarbonate and carbonate we could get from mineral sources such as calcium carbonate, for example. But so we're looking at all three of those things. Now, there are other acids out there. There's sulfuric acid and nitric acid. But in most water samples, they're not that significant. So these are the things we're looking at when we're looking at sources of acid, right? Is carbon dioxide and other acids. And this is going to come back and it's going to relate to alkalinity, which we're going to talk about next day. So I just want to spend a few more minutes kind of just talking about acids and acid rain, and then that's where I'm going to finish for today. So the second question, it says, what affects the levels of carbon dioxide and oxygen? So a big one is, of course, photosynthesis. Hopefully everybody knows the formula for photosynthesis. So in photosynthesis, we have water plus carbon dioxide. And of course, it takes light energy, and it produces O2 and sugar, right? So photosynthesis, we could say photosynthesis, I guess I didn't leave myself a lot of room. Photosynthesis consumes CO2 and produces O2. And of course, the other reaction, which I'm not going to write out, is of course cellular respiration. Respiration consumes O2 and produces CO2. So those are huge events and chemical reactions that are going on with all the wildlife that's going to be found in aquatic systems, right? Photosynthesis and respiration. The other thing, of course, is dissolved oxygen, and we're going to talk about dissolved oxygen probably next day in terms of where that comes from, because a bunch of that is coming from the atmosphere as well. But that's kind of what I was getting at here. Okay, so I want to talk a little bit about acidity and acid rain. So the first question there is, why do we care about acidity? Well, we're talking about making some relatively reactive species, the hydrogen ions. And in industrial processes, we're talking about this can mess up your chemical reactions, it can corrode equipment, those kind of things. In biological systems, it can affect life, it can affect the quality of soil, whether plants are going to grow or not, all those kind of things. I think I've already answered why it's important in the water industry. And sometimes it affects really, in terms of the processes, whether you have to adjust it by adding in buffers or neutralizing agents as well. It's also used in the wastewater industry in terms of they're looking at the acidity of their solutions and at different parts of the breakdown. And if the pH is off, the whole system is affected in terms of its efficiency. So you can see some numbers there in terms of 10 to 1 or 5 to 1 kind of ratios there. So just a little bit about acid rain. We mentioned that carbon dioxide is a source of acid in the environment. The other one is acid rain, which is something that used to be talked about a lot. It still is an issue. We have a lot cleaner industrial processes. We can see there's the definition. If rain has a pH of less than 5.65, that's the definition in Canada, it's considered acid rain. So where does acid rain come from? You can see we have SO2, which is sulfur dioxide. And SO2 combines with water the same way that CO2 combines with water, and you get sulfuric acid. And you get a bunch of nitrates and nitrates and things like that. So NO2 is nitrate and produces nitric acid. And then these things rain down, and it doesn't have to be in the same place the pollution is produced, but it can rain down and, of course, affect farms and soils and the minerals in the grounds by quite a bit. Here's another diagram showing you what parts of Canada are considered to be highly sensitive parts of Canada. And you can see it's a huge part of Canada, right? Places with, places that have carbonate bedrock. So kind of around Fort McMurray, and much of Alberta has a lot of limestone, and that will actually neutralize the acids. But many other parts of Canada don't have quite as much. So they're a lot more sensitive to the acidic pollutants. Anyway, that's exactly where I wanted to finish today. Like I said, kind of just wanted to finish talking about some of the acid base acid stuff. We're going to kind of get to the basic alkalinity stuff on Wednesday, but I'm going to stop there, and it gives you a few more minutes to brush up on anything that you may need to do for your test. And what I'm going to do is I'm going to stop the meeting now, and I'm going to restart it up in a few minutes so that if anyone wants to join in to ask any questions about the test, they can do so. But I'm not going to keep everybody on. You don't need to remain on Zoom during the test. Only just join if you have any particular questions.